Frank Press stood in his Caltech seismology lab on August 29, 1957, staring at data that made no sense. The seismograph needles had recorded a Soviet nuclear test at Semipalatinsk. That part was routine. What wasn't routine was the faint trace that appeared 30 seconds before the main seismic wave arrived. He ran the timeline again. The test detonated at 05 AQ GMT. The primary seismic waves, traveling through Earth's crust at roughly 8 kilometers per second, reached his station 387 seconds later. But this ghost signal showed up at 357 seconds, 30 seconds early. Press had been analyzing underground nuclear explosions for 3 years, long enough to know that seismic waves didn't break the rules of physics. They couldn't arrive before they left. He checked the instrument calibration, examined the recording drum for mechanical faults, even considered whether his graduate students had somehow contaminated the data. Everything checked out. The signal was real. He spent the next week correlating data from other seismograph stations across the western United States. Every station showed the same anomaly, a subtle precursor arriving ahead of the seismic waves. The pattern was consistent. Larger explosions produced stronger precursor signals. Press calculated the propagation speed of these mystery waves. They traveled at approximately 340 meters per second, the speed of sound. That's when it hit him. These weren't seismic waves at all. They were atmospheric pressure waves, gravity waves, generated when the nuclear fireball heated the air above the explosion site. The massive temperature spike created a pressure disturbance that propagated outward through the atmosphere at the speed of sound, reaching his instruments before the slower seismic waves traveling through solid rock. The explosion essentially rang the atmosphere like a bell. Press grabbed a pencil and worked through the physics. A 20-kiloton explosion would heat approximately 50,000 cubic meters of air to temperatures exceeding 10,000 degrees Celsius. That thermal expansion would generate a pressure pulse strong enough to create measurable gravity changes at the surface. Tiny variations in Earth's gravitational field as the atmospheric mass shifted. His seismographs weren't sophisticated enough to measure pure gravity changes, but they were sensitive enough to detect the ground motion caused by those atmospheric pressure waves pushing down on the surface. The implications were staggering. If you could build an instrument sensitive enough to measure gravity changes directly, a gravimeter designed specifically for this purpose, you could detect nuclear explosions 30 seconds before any seismic signal arrived. For military intelligence, those 30 seconds represented an enormous advantage. More importantly, gravity waves wouldn't be affected by the geology between the explosion and the detector. Seismic waves got scattered, absorbed, and distorted passing through different rock layers. Gravity waves traveled through air, following a direct path regardless of terrain. Press drafted a proposal that same week. He outlined the physics, included his correlation data from the August test, and calculated the required sensitivity. A gravimeter capable of detecting changes as small as 1 part per billion in Earth's gravitational field. He titled the proposal Atmospheric Gravity Wave Detection for Nuclear Test Monitoring and submitted it to the Advanced Research Projects Agency in September 1957. Then he waited. Press didn't wait for Pentagon approval. He converted a basement storage room in Caltech's seismological laboratory into a workshop, spending $3,000 of his discretionary research funds on machined aluminum, precision bearings, and a 1,000-pound lead mass. The concept was straightforward. Suspend a massive weight on a horizontal beam so delicate that even microscopic gravity changes would cause measurable displacement. The engineering was brutal. Traditional gravimeters used vertical pendulums, measuring how gravity pulled objects downward. Press needed something different, a horizontal pendulum that would respond to the lateral components of gravity waves passing through. He designed a 12-foot aluminum beam balanced on a knife-edge fulcrum, with the lead mass mounted at one end and a counterweight at the other. The entire assembly sat in a vacuum chamber to eliminate air resistance. On paper, the system could detect gravity changes of 1 part per billion. In practice, every truck passing on San Rafael Avenue created larger disturbances than a nuclear explosion 5,000 miles away. He spent 3 months eliminating noise sources. Temperature fluctuations caused the aluminum beam to expand and contract, mimicking gravity signals. He built a temperature-controlled enclosure, maintaining stability within 0.01 degrees Celsius. Seismic vibrations from local earthquakes, traffic, even students walking in the hallways above, all registered as false signals. He mounted the entire apparatus on a vibration-isolated platform using pneumatic dampers. The beam itself became a problem. It flexed under its own weight. He replaced it with a custom-machined I-beam with structural ribbing that reduced flex by a factor of 10. By January 1958, he had a functioning instrument. The readout system used a beam of light reflected off a mirror attached to the pendulum arm, projecting onto photographic paper 20 feet away. A 1 nanometer displacement of the beam translated to a 2 millimeter movement of the light spot. He could now measure gravity changes equivalent to a grain of sand added to one side of a football field. The first real test came on March 4, 1958, when the Soviets detonated a 2.9 megaton device in the atmosphere above Novaya Zemlya. Press stood in his basement lab watching the light spot. At 11:47 GMT, exactly 412 seconds after the detonation, the spot shifted 8 millimeters to the left, held for 3 seconds, then returned to center. The seismographs upstairs registered the arrival of seismic waves 35 seconds later. His gravimeter had detected the gravity wave signature, traveling at acoustic velocity through the stratosphere. He documented 12 more Soviet tests over the next 6 months, each one producing a distinct gravity wave signature that preceded the seismic signal. The wave amplitude correlated directly with explosion yield. Larger blasts produced proportionally stronger gravity signals. He could estimate yield within 20% accuracy just from the gravity wave data. In September 1958, Press received his official rejection from ARPA. The review panel concluded that atmospheric gravity waves remain theoretical constructs without experimental verification, and that proposed detection sensitivity exceeds physical limitations of mechanical instruments. One reviewer noted that gravity wave detection borders on pseudoscience given current understanding of atmospheric physics. Press had a dozen documented detections proving otherwise. He submitted his data to the Journal of Geophysical Research in October, including oscilloscope traces, timing calculations, and correlation analyses with confirmed Soviet tests. The paper was published in March 1959. Still, the Pentagon wouldn't return his calls. The Pentagon's skepticism ran deeper than Press anticipated. At a November 1959 briefing in Washington, he faced a panel of Air Force scientists who treated his gravity wave data like astrology charts. Colonel Robert Henderson, director of the Air Technical Applications Center, examined Press's oscilloscope traces with undisguised contempt. "You're claiming to measure gravitational changes smaller than the effect of a sparrow landing on your roof," Henderson said. "And you expect us to bet national security on this?" Press walked them through the physics again. A 10 megaton explosion releases energy equivalent to 10 million tons of TNT, heating the atmosphere above the blast to temperatures that would vaporize steel. That thermal expansion creates a pressure wave traveling at the speed of sound, approximately 340 meters per second at stratospheric altitudes. When that pressure wave reaches the ground, it generates a measurable gravity anomaly. "I've detected 47 Soviet tests with this method," Press said. Every single one arrived 25 to 40 seconds before the seismic waves. "Correlation isn't causation," Henderson replied. "You're probably detecting microseismic noise, atmospheric turbulence, temperature artifacts. The fact that your signals happen to arrive before seismic waves doesn't prove they're gravity waves." The Air Force had invested $12 million building the worldwide standardized seismograph network. 120 stations specifically designed to detect underground nuclear tests via seismic waves. Henderson wasn't about to tell his superiors that a single gravimeter in a Caltech basement had made that entire network obsolete. The academic physics community was equally dismissive. At the 1960 American Geophysical Union meeting, Press presented his detection data to a room of 200 researchers. During the question period, Harvard physicist Harold Jeffreys stood up and declared that atmospheric explosions couldn't generate gravity waves with sufficient amplitude to be detected at intercontinental distances. The inverse square law alone makes this impossible, Jeffreys said. Your signals are instrumental artifacts. 3 other researchers echoed the criticism. Press spent 20 minutes defending his methodology, explaining his temperature controls, his vibration isolation, his calibration procedures. Nobody was convinced. The classified intelligence community had its own objections. CIA technical analysts worried that gravity wave detection was too sensitive, that it would generate false alarms from non-nuclear sources. What about large conventional explosions? Volcanic eruptions? Meteors? Even if the physics worked, how would you distinguish a nuclear test from other atmospheric disturbances? The analysts preferred systems with clear, unambiguous signatures, seismic waves from underground tests, radioactive debris from atmospheric tests. Those were concrete, verifiable evidence. Gravity waves felt too exotic, too dependent on complex physics that might fail under operational conditions. Press tried a different approach. In April 1960, he submitted a proposal directly to the CIA's Office of Scientific Intelligence, bypassing the Air Force entirely. He requested $180,000 to build a network of 6 gravimeter stations across the western United States, positioned to triangulate the source location of gravity wave signals. The proposal included detailed engineering specifications, sensitivity calculations, and false alarm rate estimates. He argued that gravity wave detection could verify Soviet compliance with any future atmospheric test ban treaty, providing early warning before radioactive debris reached monitoring stations. The CIA response arrived 3 months later. Proposal declined due to insufficient confidence in underlying detection methodology. They suggested he continue his research and resubmit when the technology matured. Press had published data, working instruments, and reproducible results. Apparently, that still wasn't enough. He went back to his basement lab and kept recording. Press was in his Caltech office, grading midterm exams when the gravimeter alarm triggered at 8:33 a.m. Pacific Time on October 30th, 1961. He ran downstairs to the basement lab. The light spot on the photographic paper had deflected 47 millimeters, the largest displacement he'd ever recorded. The beam held its position for 9 seconds before slowly returning to center, oscillating slightly as the pendulum stabilized. Press checked his watch. 8:33:42 a.m. He marked the time in his logbook and waited. The seismograph needles upstairs jumped at 8:34:12 a.m., exactly 30 seconds later. The seismic waves showed a magnitude consistent with a massive explosion somewhere in the Soviet Arctic. Press ran the calculations based on gravity wave arrival time and amplitude. The explosion had occurred at 8:26 MOGS a.m., approximately 4,870 miles from Pasadena. The yield estimate from the gravity wave amplitude was staggering, somewhere between 45 and 55 megatons. Nothing that large had ever been detonated. He spent the next hour on the phone with the Air Force Technical Applications Center, trying to get confirmation. The duty officer told him their seismic stations had recorded a significant event in the Novaya Zemlya region, but couldn't provide yield estimates yet. Press gave them his data. Gravity wave arrival at 8:33:42, estimated yield 50 megatons based on wave amplitude and propagation characteristics. The officer thanked him politely and hung up. Press knew they thought he was delusional. The confirmation came 3 days later from atmospheric sampling. Air Force WC-135 aircraft detected radioactive debris patterns consistent with a 50 megaton atmospheric burst over the Arctic. The Soviets had detonated Tsar Bomba, the largest nuclear weapon ever tested. Press's gravity wave detection had been accurate within 4%. More importantly, his gravimeter had detected the explosion 30 seconds before any other monitoring system on Earth. He received a phone call on November 6th from someone named Dr. Carl Romney at ARPA. Romney didn't introduce himself beyond his name and title, Deputy Director for Nuclear Monitoring Research. "Your gravity wave data from the October 30th test," Romney said. "You logged detection at 8:33:42 Pacific Time. How confident are you in that timestamp?" "Completely confident," Press replied. "The alarm triggered automatically, and I witnessed the deflection in real time. The seismic waves arrived 30 seconds later." Romney was quiet for a moment. "We need to discuss installation requirements for a prototype network. Can you be in Washington on November 14? The meeting lasted 4 hours. Romney brought engineers from the CIA's Office of Research and Development, physicists from Lawrence Livermore, and Air Force intelligence analysts who'd spent 2 years dismissing Press's work. They wanted specifications for a nationwide gravimeter network, sensitivity requirements, installation procedures, power needs, data transmission protocols, false alarm rates. Press laid out the engineering. Each station needed a temperature-controlled vault maintaining 0.01 degree stability, vibration isolation rated for local seismic noise, vacuum chambers for the pendulum assemblies, and continuous chart recorders. Each installation would cost approximately $45,000. The network would need at least 12 stations distributed across the continental United States to triangulate source locations and discriminate against local noise sources. Romney asked the critical question, "Can your gravimeters detect underground tests?" Press explained that shallow underground tests, anything less than 200 meters deep, would vent enough atmospheric disturbance to generate detectable gravity waves. Deeper tests wouldn't breach the surface, producing only seismic signals. But for atmospheric and shallow underground tests, gravity waves would arrive first every time. The contract approval came through on December 1, 1961. Project budget, $640,000 for 12 gravimeter stations. Installation deadline, March 1962. The CIA wanted the network operational before the Soviets resumed atmospheric testing. Press assembled a team of 7 engineers and spent January 1962 manufacturing identical gravimeter units in a machine shop he rented in Pasadena. Each unit required precision fabrication. The aluminum I-beams had to be machined to tolerances of 0.001 inches. The knife-edge fulcrums hand-lapped until they achieved mirror finishes. The 1,000-pound lid masses cast in custom molds that prevented internal voids. The vacuum chambers alone cost $3,800 per unit. Site selection followed geology and geography. The CIA wanted stations positioned to triangulate explosions anywhere in the Soviet Union, China, or the Pacific proving grounds. Press chose locations with minimal seismic noise, bedrock sites away from highways, railroads, and urban centers. The first station went into a limestone cave outside Carlsbad, New Mexico, where natural temperature stability eliminated the need for active climate control. Others were installed in abandoned mine shafts, underground bunkers, and specially constructed vaults. The Montana installation illustrated the challenges. Engineers excavated a 12 by 15-foot chamber 40 feet underground in granite bedrock near Shelby, 90 miles from the Canadian border. They poured a 6-inch concrete floor with embedded anchor bolts, installed climate control equipment capable of maintaining 68 degrees Fahrenheit within 0.01 degrees, and ran dedicated power lines from a substation 3 miles away. The vibration isolation platform sat on pneumatic dampers filled with pressurized nitrogen. Any leak would ruin the instrument's sensitivity. Installation took 6 weeks and cost $52,000, $7,000 over budget. Each gravimeter required 3 days of calibration. Press would place known masses at measured distances from the instrument, calculating the expected gravity change and comparing it to the actual deflection. A 100-kilogram weight positioned 10 meters away produced a gravity change of 6.67 nanogals, barely detectable above instrument noise. The target sensitivity was 0.1 microgals, roughly 150 times larger than the calibration signal. Achieving that meant isolating the instrument from temperature variations smaller than 0.005 degrees, vibrations below 0.01 micrometers, and air pressure changes less than 0.1 pascals. The network went live on March 28, 1962, 12 stations spanning from Washington State to Maine, Montana to Texas. Each station transmitted data via encrypted teletype lines to a control center at ARPA headquarters in Arlington, Virginia. Press installed a master display board showing real-time readings from all 12 gravimeters simultaneously. Any deflection exceeding 0.5 microgals would trigger audible and visual alarms. The first detection came on April 2, 1962 at 3:14 a.m. Eastern Time. Stations in Montana, Wyoming, and Nevada registered simultaneous deflections of 0.8, 0.6, and 0.4 microgals, respectively. Triangulation placed the source over the Arctic Ocean, approximately 5,100 miles from Nevada. Seismic waves arrived 34 seconds later, confirming a Soviet atmospheric test at Novaya Zemlya. Estimated yield from gravity wave amplitude, 2.1 megatons. Air Force radioactive debris sampling 3 days later confirmed 2.0 megatons. Over the next 8 months, the network detected 47 Soviet atmospheric tests. Every detection preceded seismic confirmation by 25 to 40 seconds. The gravity wave amplitudes correlated with yield estimates within 15% accuracy. More importantly, the system never produced a false alarm. Every deflection above threshold corresponded to a confirmed nuclear explosion. Romney called it the most reliable nuclear detection system ever deployed. Press kept detailed logs of every detection: timestamp, amplitude, calculated yield, source location, seismic arrival time. The data would prove crucial when negotiators began drafting treaty verification protocols. For now, the gravimeters simply watched and recorded while the Soviets detonated weapon after weapon into the atmosphere. The Soviet testing tempo accelerated through summer 1962. Press's network logged explosions on June 20th, July 8th, July 19th, August 5th, yields ranging from 150 kilotons to 19 megatons. Each test produced a distinctive gravity wave signature. Rapid onset as the fireball heated the atmosphere, peak amplitude correlating with total yield, gradual decay as the pressure wave dissipated. The Montana and Wyoming stations, positioned to monitor the Arctic test sites, recorded the clearest signals. Nevada and Arizona stations picked up fainter traces, confirming the waves propagated globally at acoustic velocity. The August 27 test demonstrated the system's strategic value. At 7:22 a.m. Eastern Time, the Nevada station detected a 1.2 microgal deflection, but Montana and Wyoming showed nothing. Triangulation placed the source south-southeast of Nevada, not Siberia. The Soviets had detonated a weapon over their Seryshagan test site in Kazakhstan, 1,900 miles closer to the U.S. network than their Arctic facilities. Press calculated the yield at 300 kilotons based on amplitude and distance. Seismic stations struggled with the reading. The explosion had occurred at high altitude, where seismic coupling was minimal. The gravimeters provided the only reliable yield estimate. By September 1962, Press had accumulated enough data to establish quantitative relationships. Gravity wave amplitude was directly proportional to yield raised to the 0.67 power. A 10 megaton explosion produced a signal 4.6 times stronger than a 1 megaton blast at equivalent distance. Wave amplitude decreased with distance following atmospheric absorption models, roughly inverse square for the first 3,000 miles, then more gradual decline as stratospheric propagation dominated. He could now predict detection thresholds. His network would reliably detect any atmospheric explosion above 50 kilotons anywhere north of the equator. The strategic implications crystallized during the Cuban Missile Crisis. On October 28, while Kennedy and Khrushchev negotiated the withdrawal of Soviet missiles, Press's gravimeters logged 3 atmospheric tests at Novaya Zemlya, yields of 8.5, 1.2, and 12.7 megatons. The Soviets were demonstrating their nuclear capabilities even as they publicly pursued de-escalation. The gravity wave data reached the White House within minutes of detection, 30 seconds before seismic confirmation, 4 days before radioactive debris sampling. Kennedy's national security team had real-time intelligence on Soviet nuclear activities during the most dangerous confrontation of the Cold War. The testing pause came in November 1962 after both superpowers had demonstrated their arsenals. Press's network had logged 47 Soviet atmospheric tests and 22 American tests at the Pacific Proving Grounds. The data archive revealed patterns the CIA hadn't anticipated. The Soviets conducted tests in clusters separated by 8 to 12 days, suggesting specific operational schedules tied to weather patterns or strategic planning cycles. High-yield tests above 5 megatons always occurred at Novaya Zemlya's northern test site, while lower-yield tactical weapons were tested at Semipalatinsk. More valuable than the detection statistics was the confidence the network provided. Air Force analysts now had an independent verification method that operated continuously, required no aircraft overflights, and provided yield estimates before any other system. When treaty negotiations resumed in early 1963, American negotiators could propose atmospheric test ban terms, knowing they possessed reliable verification capability. The Soviets could test anywhere on their territory or in international airspace. Gravity waves would arrive at Press's stations 30 seconds ahead of everything else, carrying a complete signature of yield, location, and altitude. The network had transformed from experimental physics into operational intelligence infrastructure. The limited test ban treaty negotiations began in Moscow on July 15, 1963, with a fundamental problem. How do you verify an atmospheric test ban without inspectors on Soviet soil? Seismic monitoring worked for underground tests. Radioactive debris sampling required days or weeks, and satellite reconnaissance was still experimental. Press's gravity wave network offered something unique: verification that was instant, reliable, and unambiguous. The first violation signal came on December 2, 1963, 3 months after treaty ratification. At 4:47 a.m. Eastern Time, stations in Montana, Wyoming, and Nevada simultaneously registered deflections of 1.2, 0.9, and 0.6 microgals. Press was at the ARPA Control Center within 20 minutes. The triangulation pointed to Semipalatinsk, but something was wrong with the signature. The gravity wave showed the characteristic rapid onset of an atmospheric explosion, but the amplitude was weaker than expected for that distance, suggesting either a low-yield test or an attenuated signal. Seismic data arrived 35 seconds after the gravity wave detection. The seismographs showed a strong underground signal, magnitude 5.2, consistent with an explosion 150 to 200 meters below the surface. But underground tests shouldn't generate gravity waves. Press pulled the gravimeter traces and studied the waveform. The initial deflection was sharp, atmospheric heating from a fireball breaking the surface. The Soviets had conducted a shallow underground test that vented. He calculated backwards from the gravity wave amplitude and seismic magnitude. The explosion yield was approximately 8 kilotons. At 150 meters depth in competent rock, 30 to 40% of the explosion energy would have vented through fractures to the surface, creating a thermal plume hot enough to generate detectable gravity waves. The seismic signal confirmed the underground component, while the gravity wave proved atmospheric venting. Together, they indicated a treaty violation. Underground tests were permitted, but venting radioactive debris into the atmosphere was prohibited. Press drafted a technical report and delivered it to the CIA's Office of Research and Development on December 3rd. The analysts were skeptical. Could he prove the gravity wave came from venting rather than some other atmospheric disturbance? Press walked them through the physics. The signal timing matched the seismic event precisely. The waveform showed thermal expansion characteristics, and the amplitude-to-distance ratio was consistent with an 8 kiloton surface burst. A natural atmospheric disturbance wouldn't correlate with a seismic event at the exact same location and time. The CIA dispatched a U-2 aircraft to sample the stratosphere over Kazakhstan. 6 days later, lab analysis confirmed radioactive isotopes consistent with fresh nuclear debris, specifically cesium-137 and strontium-90 ratios, indicating a low-yield fission device. The Soviets had violated the treaty, probably unintentionally. Shallow underground tests were notoriously difficult to contain, especially in fractured geology, but the violation was real. State Department officials debated whether to confront Moscow. The evidence was solid: gravity wave detection, seismic confirmation, radioactive debris sampling. But revealing the gravity wave capability would expose a classified monitoring system the Soviets didn't know existed. Press argued for disclosure. The treaty was worthless without enforcement, and the gravimeter network was valuable precisely because it could verify compliance. The State Department disagreed. They filed a confidential diplomatic note citing atmospheric monitoring data without specifying the source. Press's network detected 3 more venting events over the next 18 months, all at Semipalatinsk, all shallow underground tests between 100 and 200 meters depth. The Soviets eventually moved their underground testing to Novaya Zemlya, where deeper geology prevented venting. The gravity wave detections continued, but now they only registered Soviet atmospheric research explosions in unpopulated regions, tests technically permitted under treaty exceptions for peaceful purposes. Press logged them all, building an archive that proved the monitoring system worked. The Comprehensive Nuclear Test Ban Treaty negotiations in 1965 brought Press's gravity wave network into explicit treaty language for the first time. American negotiators proposed verification protocols that specifically mentioned atmospheric pressure wave detection systems as acceptable national technical means of monitoring compliance. The Soviets objected initially, arguing that such systems couldn't distinguish nuclear explosions from large industrial accidents or natural phenomena. Press provided the data that settled the debate. He prepared a classified briefing document analyzing 127 nuclear explosions detected by his network between 1962 and 1965, 69 Soviet tests, 36 American tests, 18 British tests, and 4 French tests. Every nuclear explosion produced a gravity wave signature with 3 distinctive characteristics that industrial accidents couldn't replicate. First, the rise time. Nuclear fireballs reached peak temperature in 0.3 to 0.8 seconds, creating near instantaneous pressure waves. Chemical explosions took 2 to 5 seconds to develop peak pressure. Second, the amplitude-to-duration ratio. Nuclear gravity waves showed high amplitude with short duration, typically 3 to 9 seconds. Industrial explosions produced lower amplitude signals lasting 15 to 30 seconds. Third, the spectral content. Nuclear explosions generated pressure waves with dominant frequencies between 0.2 and 0.5 Hz, while chemical blasts showed broader frequency distributions. He included comparison data from non-nuclear events his network had detected. The April 1964 Great Alaska Earthquake generated measurable gravity waves from crustal displacement, but the signature was entirely different: low frequency, long duration, gradual onset. A 500-ton conventional explosive demolition in Nevada produced a barely detectable signal that looked nothing like a nuclear test. Meteor atmospheric entries created pressure waves, but they showed supersonic propagation characteristics and came from trajectories inconsistent with ground-based sources. The briefing convinced Soviet negotiators that gravity wave monitoring was technically sound. What sealed the treaty was Press's demonstration of the system's limitations. He explained that gravimeters could only detect atmospheric and venting underground tests. Fully contained underground explosions below 300 meters produced no atmospheric signature. This meant both sides could conduct underground testing for weapons development while maintaining a verifiable ban on atmospheric tests that produced fallout. The Soviets accepted monitoring they couldn't evade while preserving their ability to continue weapons research underground. Treaty ratification in 1966 transformed Press's experimental network into permanent verification infrastructure. The CIA expanded the system to 23 stations, adding installations in Alaska, Hawaii, and Greenland to improve coverage of Soviet Pacific and Arctic test sites. Each new station followed Press's original design specifications with incremental improvements: better temperature control using thermoelectric cooling, digital data recording, replacing chart recorders, automated signal processing that could distinguish nuclear signatures from noise without human analysis. The network's operational success established gravity wave detection as legitimate science. The same physics community that had dismissed Press's work in 1960 now cited his publications as foundational research. Stanford and MIT launched their own gravity wave research programs, not for nuclear monitoring, but for earthquake prediction and atmospheric physics. The National Science Foundation funded a civilian gravimeter network for geophysical research, using instruments derived from Press's military designs. By 1968, gravity wave detection had become the primary verification method for atmospheric test ban compliance. The network had logged over 400 nuclear explosions without a single missed detection or false alarm. When France conducted atmospheric tests in the Pacific, Press's gravimeters detected them 4,200 miles away. When China detonated weapons in Lop Nur, the network recorded every test despite the remote location. The system that Pentagon officials had called pseudoscience 7 years earlier was now the most reliable nuclear monitoring capability the United States possessed. Press received the National Medal of Science in November 1974, presented by President Gerald Ford in a White House ceremony. The citation credited him with revolutionary contributions to geophysical monitoring and international security through the development of gravity wave detection methods. The classified details remained secret. Ford couldn't mention that Press's instruments had detected 600 nuclear explosions over 12 years, providing verification data that made arms control treaties possible. But everyone in the East Room understood what the medal really represented: vindication for the seismologist who'd been laughed out of Pentagon briefing rooms 15 years earlier. The academic recognition came earlier and meant just as much. MIT appointed him institute professor in 1965, the university's highest faculty rank, reserved for scholars who'd fundamentally advanced their fields. His gravity wave papers were now required reading in geophysics graduate programs. The instruments he'd built in a Caltech basement had evolved into a worldwide monitoring network operated by the Air Force Technical Applications Center, with 47 stations on 6 continents detecting explosions anywhere on Earth above 10 kilotons yield. The scientific legacy extended beyond nuclear monitoring. Press's gravimeter design became the foundation for modern superconducting gravimeters used in earthquake research, volcanic monitoring, and geodesy. His work on atmospheric pressure waves contributed to tsunami warning systems. The same physics that detected nuclear fireballs also applied to ocean displacement from submarine earthquakes. NASA adapted his instruments for planetary gravity mapping missions. The Apollo 17 crew deployed a gravimeter based on Press's design on the lunar surface, measuring the moon's gravitational field with unprecedented precision. What Press found most satisfying wasn't the medals or appointments, but the complete reversal in how scientists and intelligence officials viewed gravity wave physics. The Air Force officers who dismissed his work as instrument artifacts now sent their analysts to study his methods. The CIA declassified portions of his early detection data, allowing him to publish comprehensive analyses in academic journals. Harold Jeffries, the Harvard physicist who declared gravity wave detection impossible, wrote a formal letter in 1970 acknowledging his error and praising Press's experimental rigor. The human cost had been real. Press spent 6 years fighting institutional skepticism while watching the Soviets detonate hundreds of weapons he could detect, but couldn't convince anyone else to take seriously. His marriage nearly collapsed under the pressure. His wife later told interviewers that Frank would disappear into his basement lab for 16-hour stretches, emerging only when his gravimeter alarm triggered. His graduate students learned to work around his obsessive focus on a project most senior scientists considered a dead end. But the breakthrough, when it finally came, validated everything. The Tsar Bomba detection in October 1961 proved the physics worked at continental scales. The CIA contract transformed theoretical research into operational capability. The treaty verification success demonstrated that arms control didn't require trust. It required physics. Press had shown that you could monitor compliance with treaties through instruments that measured reality at the precision of 1 part per billion. He died in 1994, 2 years after the Comprehensive Nuclear Test Ban Treaty was opened for signature. The treaty's verification annex explicitly listed gravity wave monitoring as an approved national technical means of detection. Every station in the global network traced its design lineage back to the 12-foot aluminum beam Press had balanced in his Caltech basement. The network that began with a single seismologist noticing an anomaly in Soviet test data had become the foundation for verifying nuclear restraint worldwide. The Pentagon officials who'd rejected his proposals never apologized. They didn't need to. The instruments spoke for themselves.